Perfect. Okay, good.
Hello everyone. So today I will present you the paper Gossip Planning with Linear Model on Fully Distributed Data, which was written by Ormandy, Egigus, and Gelicity. So the main idea of the paper is to present a decentralized machine learning algorithm. And if you have seen the previous talk about predicate learning, it's a bit similar, but here we have fully decentralized topology. We are on a peer-to-peer network, so there's no central server or central authority. And in fact, this paper has been published in 2013, so it was 4 years before the first paper on predicate learning by Mohamed and the team at Google. And before this paper, there was already some works about peer-to-peer machine learning. But here, the main idea is that we are on a fully decentralized data model. I will explain what it is in a few slides. And each node communicates only with his neighbors in a gossip manner. So, what are the motivations? Why do we want a decentralized machine learning model instead of a centralized one or a federated one? And what goal do we want to achieve? So, in the same idea as in the federated learning, we are focused on privacy. So if you have a classic centralized machine learning model, you need to aggregate to all the data on one server or one group of servers controlled by the same entity. And of course, you don't have any privacy, or you need to have cryptography or other tools to achieve this. And with gossip learning, we can achieve privacy because each node stores only his own data and doesn't share with other nodes his private data. And it's even more private than in the federated one because we don't have a central server that aggregates all the data of the model. And each node is only aware of his neighbors. He's not aware of all the network. And also, another concern is about the cost of computation. When you want to build a machine learning network in a centralized way, if you want to build a big neural network, for example, you need a lot of computation, a lot of data. And with federated learning, and also with gossip learning, you can do it with very few computing power because the computing cost is shared between all the nodes on the network. And one of the difference with private federated learning is that there's no central server, so it's more robust. Even if some node crash, we want the gossip algorithm to continue to run, and we want the algorithm to be resilient to churn. So churn is the idea that some node will quit the network or join the network in a random manner, and we want also the system to be scalable. So when you have a federated learning model, you have a central server. So if you have too much nodes, and too much clients, of course, there will be a scalability issue on the server. But here, because we are in a fully peer-to-peer manner, we expect the model to be more scalable and to run even with 100,000 of nodes. So in the paper, we identify three main components, necessary components to achieve gossip learning. The first one is random walk, and the idea is that because the data cannot move between nodes, it will be the model that will move, that will move on the network, across the network. And in the algorithm present in the paper, we use gossip-based pair sampling to achieve uniform sampling. The idea is that when you want model to move across the network, you want to have this random walk, and to have this random walk, you need to have an uniform sampling. You want the model to move from node to node in a uniform manner, and to achieve this, the paper use a pure sampling algorithm also based on gossip. I will not enter into details about this algorithm, but the idea is that you exchange with your neighbors your list of neighbors. So you change your neighbors with time, and so the network evolve with time, and it's like an uniform random network. The second component is online learning. So in classical machine learning, you have all the data, and you have the algorithm will learn on all the data in a one-shot manner. In contrary of this, online learning is the idea that you will learn step by step. You receive each data point one by one, and you learn and you get better with each data point. And we need this with online learning because, of course, we cannot learn on all the data because we don't have access to all the data. The model will work in the network, as I said, and each time they get to one new node, they will be updated on this data point, on the data points on the node. And the algorithm we use in the paper, which is used in the paper, is the classical stochastic Gaussian descent. And the last component that we need is ensemble learning. And the idea of ensemble learning is that we will combine several weak machine learning model to form a stronger one. And here in the paper, they use a merging method of model to achieve this ensemble learning method. And I will explain how it is done in a few slides. So before I spoke about the fully distributed data model. So what is it? It's the idea that each node has only one data point, one signal report. So it's a bit particular, but there is some real use case for this assumption. For example, we can imagine that we have one report that is really linked to one person, one user. For example, one personal profile on social network, or maybe the search history of a user. And as I said, because the data cannot be moved, we will need a model to move between nodes. And because we only have one data point on each node, we cannot achieve local learning. So if you have a few data points or even more on a local device, you can do classical machine learning only on your data. But if you only have one data point, you cannot learn because you only have one data point. The only thing we can do with the data is to update a model. when a model come up to a node, it will be updated on this unique data point. And each time it will come to a new node, it will be updated again until we achieve convergence. And because we only do this update, which is on one data point, it's extremely fast. And so we assume that we can neglect that the local computation time will be negligible compared to communication delay. And this is why in the paper, they use, they compare performance as a function of message sent between nodes and not just the time for to achieve convergence. And of course, this model also works when you have multiple data points on one node, but the more data you have on one node, the less it will be logical. So I don't know if you see it well, but this is the algorithm. It's very simple. You first init your model, each node and the network have the same model initially. I mean, it's and at each round, you select a pair and you send your model to the pair, your last model to the pair. And when you receive a pair from a model from another pair, you create a new model by combining this new model you receive with your own model to create a new model. And you do this operation in a loop. So every node waits the same amount of time, but they are not synchronized. And every node is connected to several pairs. So how the creation of model work? In the paper, they present three ways to create a new model. The first one is called create model on the mode. And in this procedure, you don't fuse the model, you don't merge the model, you just take the new model of your that you receive from your pair, from your neighbor, and you update it on your local data. And you have here to create model MU, so merge and get. You first merge the two model, your own model of the model from your neighbor, and then this new model you update it on your local data point. And create model UM, it's the opposite. You first update the two model on your local data point, and after this you merge the two updated models. And for the merge procedure, it's just the average of the parameter of the two model, or the weight. If it's a no network, for example, it will be the norm weight. And that's it for the creation of the model. And for the update itself, the update procedure, the paper presents two models, two machine learning model. The first one is add line perception. So it's a very simple linear model used for binary classification. And you have here how the update work. And it's just you compute the matrix multiplication between the weight and the data point, and you subtract the image, and you implement like this your weight. So it's a very simple model, Um, and we have also Pegasus, which is a super vector machine, CDM, and also used for binary classification. It's a bit more complex, but it's still a simple model compared to big neural network that we have now. And the paper proved that in the case of Adaline, the merge of each new stream of model is equivalent to the averaging of all model of owners. So we can imagine that in the ideal case, what we want to do is get all the models from all the nodes in the network and do an average of all these models to have the big model that represents the model of all the network. But of course, it's not feasible in reality because we'll need to store a lot of models and we will have to communicate with all the nodes in the network at the same time. So the goal of gossip planning is to achieve something like this, but in a cheapest way. And we can prove that with Adaline, because it's a linear model, when we receive a stream of model, or when we do the merge of this model, the average of the weights, when we have we will converge to the same model that we will have if we have average all the model of all the nodes. And this assumption doesn't work for Pegasus because it's not a simple linear model, but this explanation give us an idea of why we want to do this with gossip planning. And in the paper, they say that create model UM. So first we update the two models and then we merge them. Will be better than MU in the case of Pegasus. We've seen the experimentation that it's not really the case.
Why is this? Sorry, what part of the theory suggests that UM is better than MU?
Good questions. I don't remember, honestly, but this was said in the paper.
Is this related to the form of the perceptron that we use?
A bit, but I think it's that because you first update and then you merge, you will converge faster. I think if I remember, it was because of this.
Okay.
So for the experimental setup, so they use to test the algorithm. It was I say experimental the simulation. They use three data sets: returns, spin-based, and magnitude URLs. So returns is text from the returns database. Spin-based, it's a database of emails, and some of them are spam. And malicious URLs is also a database of some URLs, and some of them are supposed to be malicious. And here we are in the simulation, they compare the gossip algorithm, especially the Pegasus one, because it's more interesting than Adaline, to weighted begging. So weighted begging method it's like an averaging of all the model. The idea that you collect all the model and you compute inference on all the model and you do a vote to select your answer for the classification. But as we said, it's not feasible to collect all the model. So here the gossip algorithm I compared to this ideal case, but we cannot implement it in reality. The evaluation metric used is a 0-1 error. So it just the number of misclassified test example divided by the total number of test example. And another evaluation matrix, the positive similarity. It's the similarity between the model. And we suppose that with time, all the model will converge to the same model, all the model on all the nodes, because of the deposit timing. So we use percent similarity to measure the time we need to get convergence. And in the simulation, they have message drop. So when a node sends a message, we do an exchange to send this model to one of the node. The message can be separate. And also we have churn. So we have some node limiter that go out to go in. And we have this result, or the more results are selected is through a schema. And on the first picture, what you can see on the bottom, you have the Pegasus centralized model, so it's the baseline. And there's no cycle because we have all the data we converge in one shot. But we have this baseline to compare the observer method. So what we can see is that the weighted Bayesian method converge faster because they are the ideal case, and the Pegasus peer-to-peer Pegasus MU converge faster than on the board. Because in the case of random walk, we don't merge the model. We only get the new model from one pair new updated on our data. So this experiment, it's confirmed us that the merging of model accelerates the convergence. And we have the paper says that all the model converge, but the only difference is speed convergence. And in this second experiment, they have compared peer-to-peer Pegasus MU and UM, and we see that MU seems to converge faster, and we even get below the baseline, which is very interesting. But I think it's in the papers it doesn't conclude that MU is always better than UM. It's they say that it's equivalent. I think it's dependent on the data, the network, because there's a bit of randomness, of course, in this experiment. But they only conclude that the two methods are very similar in terms of results. Yeah. And before going to the conclusion, I want to spoke on another paper, which is the follow-up on with the same authors that compare federated learning to this. So local model and do the average. So and the server, each client updates his local model and send it to the server, and the server computes the mean or to all the model, and send back to all the clients the new version of the model. And in this follow-up paper, the authors, they compare gossip learning with federated learning, and what they show in their experiments, in their simulation, is that all the model converge, and that's also that the cohesive learning is slower than federated learning, which is not a surprise because we have a decentralized network, and so to get the model from the most from some other nodes, it can take time compared to a centralized star network when what we have with the federated learning where the central server aggregates all the nodes in one shot. But what the paper said is that when we have high compression rates, so in this paper, in this follow-up paper, what they also do is that they compress the model. They don't sound raw model, but they compress the data. Their results show that when we have high compression rates, there's similar results between gossip learning and federated. It's not in this schema, but what we say in the paper. But in the schema, what you have the slowest one is SGD. So when we learn on local data point, without doing federated learning or gossip learning, and we have federated learning that is the fastest converge, and gossip learning is a bit slower, but still they both converge. So in conclusion, for me, gossip learning is an interesting alternative to federated learning and to centralized learning, but it's still a new area of research. So as I said, the first paper was published in 2013, but there was not a lot of following works. It's only after the publication of papers about federated learning that people start to look at gossip learning. And there's still a lot of work to do. Speed of convergence, as I said, it's a bit slower right now. There's not a lot of work about implementation, it's only simulation, and not a lot of work about use case. And also, the only work I've found, I think, are only about supervised learning. So there's a lot of work about other machine learning contexts. And the big idea, of course, is can we use this architecture, this algorithm, with big model like we see ChatGPT and the big neural network model? Because, of course, it can be very difficult to even to do one update when you have millions of parameters and to send the model when the model is very big. So we cannot use it like this. We need to adapt it. And my work, so Sebastian and Maria, is about security, because when you have a network, of course, you can have malicious participants that want to destroy the work of the other participants, Byzantine. And so there's a lot of work about this subject. And that's it.
Thank you very much. So how do you know if many people connected? So if somebody has a question, questions here.
The question was the figure there was a weighted lagging. How is it weighted?
I don't remember.
There are two weighted.
The two, yes. I don't remember the difference. We can see that the first one is converged instantly because I think the difference, if I remember, that the first one we have already all the model, but the second one is a bit different. But I need to look at the paper to remember what's the difference and how exactly it's weighted.
I have 2 or 3 questions.
Yeah.
The first one is on this plot. So when they are evaluating this performance, they are taking the model where, like at this point of time, every node in the network has a different model.
Yeah.
So how do they plot this? Is like the average 0-1 error averaged on all the participants, or they chose a node and they looked what happens at this node?
When they say that they took 100 nodes by random and they compute the average.
Okay, how many nodes they have in total, ballpark?
I don't remember.
Like it's 10% of the total nodes or 1%? Well, okay, I will look at the paper. So I imagine they have very big differences between nodes in different parts of the network. So it would be nice to see how the dispersion goes. So when they speak about convergence rate, they speak about the time every node in the network gets the same model, right?
Yeah, and also we want to have the smallest 0-1 error value.
Okay, so they have two kind of convergences here that somehow are
related.
Yeah, seem to be. And the other thing that is somehow surprising to me, do you know if this has been tried with different kinds of networks? Because if everything is linear, this is gossip, so I expect that give it enough time and everybody will converge to the same thing. But here, it seems to me that if you have a very highly nonlinear model, what could happen is that the order that you do your training changes the results. So it's not, I mean, the fact that this thing converges is somehow a good news, but it was not exactly
expected.
Maybe expected, but not so straightforward. And so I was wondering if there are works that try different kind of networks or varying the functions of the perceptrons to see if there is what is the impact of the order with which you see your data in your, I think even in I'm not sure because I'm not doing machine learning, but I think if you train a model with your data, if you scramble the order of the data, you change the results somehow.
Like for me, like in the papers, they prove the convergence for the Baker's algorithm. So they prove that after some time you will converge, but you have no idea of the time of convergence. I think also you need uniform sampling to achieve convergence. What they say. So this is
maybe this is the assumption that I'm missing. I'm not really sure what their uniform sampling is, but okay.
If you have uniform sampling, you are, yeah, I think you are sure to converge in this case. But of course, if you have like very different data, you can go in direction that's it's not the minimum, or you will be stuck in a local minimum. I think it can happen.
Mm-hmm. And another thing that would be interesting is to see is the impact of these data losses that you have. I think that if they have uniform data losses and uniform sampling and the data losses are not big enough, probably you don't see it here, but it's an interesting, well, I'm asking myself, is this a way to kill this algorithm or not? And finally, if you are fishing for use cases, maybe we can have a talk outside the room, because I think we can come up with something reasonable as a use case, and maybe it's useful for you.
Okay.
And I had other questions, but I forgot them, so I will ask them in another time, like offline. So thanks a lot.
Yes.
I have two questions.
Yeah.
So how does the node join the peer-to-peer network? So does it use, for example, DHT algorithm or things like that? Or
So yeah, if we go back to the algorithm here, we just suppose that we have a function select pair that give us a pair that we can send the model to. So in the paper, this function is implemented using the gossip-based peer sampling algorithm called newscast. And in these algorithms, you suppose that the first time to join the network, you need to contact a first node.
okay.
It can be any node you need to.
Okay, and my second question is about security. Is it possible to encrypt the model using algorithm and do the operation in an encrypted way? For example, like homomorphic encryption, so that you protect the model. So, for example, you have the merge operation. Is it possible to create a merge operation that's handled with two cipher models for the data?
I think it's possible. I mean, the merging, as you have seen, it's just average to models, so it's not that complicated. But you will need to check the cost computation first. I think like homomorphic encryption is a lot of computation. I don't know if you can. The idea of gossiping is that you want also to do it on smaller device. So check.
Another issue is that when you use homomorphic encryption, what you do there is if you have an issue, you send the model to if you encrypted everything, but it will be that directly. Yeah.
So is that honest majority enough? Or you need more than like?
Well, what is that algorithm? Because you don't contain anything.
What do you mean?
Each model brings a random.
Yes.
And then we want to include it if we want to have everything.
Yeah, but okay,
But some of them
I'm taking the assumption that if you do like that, you take enough time, you converge to something good if everybody plays nicely. And my question was, like, do you need half plus one playing nice, or you need a lot more than that? Maybe you didn't test it yet.
we don't know that.
Okay. But yes.
Yeah, and this algorithm, they don't take into account malicious at all. So
yeah, I imagine.
Even like it's dependent on the malicious. If you have dumb malicious, it will not have a lot of impact. But maybe we are doing tests. But if you have smarter malicious or some coordinated malicious, it can have a bigger impact. We need to test it, but I think it's the assumption.
Anyway, when you combine, you always average the weights, basically.
Yeah, in this one. You can imagine more complex merge method that can be more resilient to Bayesian
So should be as resilient as a regular Gaussian. If the only thing that you do is averaging, well, I don't know. I forget.
And for your question, like what can be useful for accurate encryption can be useful when you want to protect the privacy, because with some attacks you can get back the data from the bidate. So encryption can protect from this attack, but as Sebastian said, it's not it doesn't protect against Byzantine, and even worse, it's more difficult to detect Byzantine if you encrypt the model. If the model are unencrypted, you can look at the data to see if it's a normal update or if it's a strange update. But if it's encrypted, you cannot. It's more difficult to detect it, I think.
Okay. And what kind of encryption is the encryption? Can you use so what is the less powerful device that can be used in a reasonable way for take a receipt and figure it down?
Good question. You mean with encryption?
Yeah. So because you are talking about privacy and security, I suppose that you have a minimum device in terms of performance.
I'm not an expert in IoT, but like I think you need a minimal amount of computing power, or maybe it will take more time to create to do local computation, so to converge more slowly. I think it's also depends on the size of the model. If you have big model, you cannot do it on the IoT device. Other questions?
Just one about online learning. So the assumption that I'm making is that every one of these users has a data point and the classification label available, right?
Yeah. Here it's binary classification, so it's
yeah. So I have the data points, but also the ground truth.
Yeah.
Okay. And so the idea is that there's sometimes you have the ground truth and sometimes they will have not. Who is using the model at the end?
Like, I think the idea that everyone that is participant of the network want to use the final model. The idea that we all participate, we all share our computing power and data sets. We don't share the data, but we use it. And also at the end, we have all similar model that is performant and general as well, and all the data.
I think I might have a nice use case here. Thank you. So if there are no other questions, thanks a lot again, Mohamed.